All right. Welcome back to another session of ME470. This is class 21. Normally this is called Welds 1 and there'd be a Welds 2. I decided to remove Welds 2 this semester. So this will be the only class that we have on the basic welding. So welding is a really important topic to include in this course, in my opinion. Sometimes it gets left out. I decided that's important enough that we cover it. There's two basic shapes, or two different basic connections between welding, welded parts. There's the fillet weld, and now we could actually, there's a couple different names for this over here. I refer to these as butt welds because you're butting up two pieces of plate, so you're joining them in line with each other. So now a bunch of different plates become one big plate, if you will. Also, if you have the flange of, like, say, an I-beam, and you want to extend the I-beam, you would butt up not only the flange but also the web, and you connect these on a ship. You can imagine there's lots of these on the hull, on the outside hull, but then you have a lot of fillet welds where you're welding two pieces of plate that are perpendicular to each other. There are other different types of welds, but welding arrangements, but these are really the two basic ones that are going on here, and they share a lot of things in common. For one, there's this, the weld digs, you got to picture it, it digs deep into the two welded parts. So they, in essence, become one. And you want enough penetration. So as you're seeing over here in the fillet weld, you actually want a deeper penetration than this. So like if you have a weld onto the other side right here, that the two would merge. That's just generally speaking what you would want to do, but it depends on what the purpose of the weld is. If it's not a strength weld, if it's not something that where it's structurally holding the pieces together, the nature of holding the metal together, there's not like a stress in that location. You might not weld it continuously and have it perfect like this, but let's just pretend that we, for the most part, we would want that trait, right? For just generally speaking. So we measure things by the leg height right here. You see that thing called the leg. So when we're defining how big a weld is, we use that leg as the main thing to measure. So when we size the thing, that's the leg. But it's actually the throat that we most often use to calculate for stresses. So you'll see that coming up pretty soon. We also should know about this important thing called the heat affected zone, or the HAZ. That's going to change the strength calculations that we make, because around the weld, the metal, whatever metal that we're welding together, it generally will have some type of heat treatment which makes it stronger. Well, as soon as you weld it, that heat treatment goes away. So in the heat affected zone, generally speaking, is where a weld is going to break. And it's actually not the weld material that'll break, but the pieces that are it's welded to. Those plates are the thing that's going to break first. Usually it's weaker than the weld material, and that's specifically because the heat affected zone right here has a source of weakness. Now, we could do things in terms of the pre-treatment and the post-treatment of welds. We could actually heat them up, and then we can cool them down at a different rate, so that will maintain some amount of heat treatment. But we have to recall that heat treatment is in materials is generally pretty closely maintained. But when we're outside not outside, outdoors, but we're not in a foundry, we're not in in the place where the metal is being closely monitored, and that we have a systematic and repeatable processing of the materials. It's usually going to be in a machine shop, or even at the location of where it's being built, or it could be in a shipyard. And under those conditions, it's much more difficult to be able to control the tempering process, or the quenching process that we want to put in, and the granular growth of the material, right, as it starts to cool down from its the high temperature, come back down to a low temperature. That's going to create grain growth, and to be able to control that after you're done welding it's going to not give you the same amount of heat treatment that the plate had originally. Over here on the groove weld, which I often refer to as a butt weld, because you don't necessarily have to cut a groove into the pieces, but often you do. You'll grind away and maybe make a little section for a place to be able to weld these two pieces together. This is also showing with a backing bar in there, and you don't always have a backing bar. So this is not a universal thing, but quite often there will be a pre-treatment, and we will make a groove in between these two plates that are butting up against each other. It too has a heat affected zone. And most often, this throat is going to be right here across the piece. So just to give you sort of the generalized look at what these two configurations are going to be and things you should know. Now, the welding I'm most familiar with is SMAW, or stick welding, which is shield metal arc welding, where you have these electrodes that come in boxes, and they're really coated with this ceramic type of material that will heat up and melt away. And as it's melting, it makes this gas that protects the molten metal. The combination of the electrode melts away, and it's the filler material. So you're heating up the work and it is starting to melt and pool, a little section of it, but also the electrode is melting, and at the same time, there's gas that's sort of like making this protective little shield that's keeping oxygen from bonding with the molten metal, because that you could have, like, you could imagine interior kind of corrosion that would happen, which would weaken the weld. So we need to have this type of shield taking place right here. So that's the shielded metal arc welding, or the stick welding. It's probably I wouldn't say the most common, but it's the most straightforward one. Like, if you're going to do a small amount of welding, you would get a welding machine and get a bunch of different electrode sticks. And there are all kinds of different electrodes for different tasks. There's some generalized ones that you might become familiar with. The 6010 and the 6011. We'll talk about what those numbers mean, but those are the most common. Also a 7018. That's also a very common. And those numbers mean a thing. Mean something. But here's the arrangement that you usually have: is you have this welding machine, you get some kind of power source, and you have two different leads. One's connecting to, this will be a steel table, by the way, this welding table. And sometimes you'll actually even connect this, make sure there's a really good connection between your piece of your welded material and the table. It just shows it laying right here. You might have a clamp on there, and you might take a grinder to both of them to make sure this is a really good electrical connection between the welded piece and the ground. And then you have this electrode holder here. This is also often called a stinger, and it's clamping the electrode in there. So almost like a little pair of pliers. And what you do is you get the right amperage setting on your welding machine that's correct for the thickness of the piece and the type of electrode, and then you proceed. I think I'm going to give the big picture. The very most important thing that you should know about the act of welding is its maintenance of heat and its manipulation of the heat that's necessary, and just enough but not too much to be able to make a good bond between whatever you're welding, and the pieces that you're welding together, and the electrode filler that you're putting inside. So as you're dragging this electrode along, you can see that they're showing the ceramic coating on here. It's starting to turn into the shielding gas. And what you're chasing is this little puddle of metal. You're chasing it around. It's a combination of the base metals and the electrode filler metal. And as it's going along, it's starting to cool, and we're usually making a shape that looks like these kind of crescents. Now, there's lots of different types of welding patterns, but the most often is to come back in a zigzag with a little arc back and forth. And what you're one very pretty weld, a really pretty weld, will look like, I've heard it described as a stack of dimes, right? That you're laying down. That's going to be a good looking weld. They show one over here. I picked this one out, but this isn't really that beautiful of a weld. And by the way, stick welding, it's a little more difficult to get that beautiful, perfect weld than like with a TIG weld or with a MIG weld, and we'll talk a little bit about that. But it's the manipulation of this puddle and the speed at which you do it, and this angle actually matters too. But the most critical thing is this gap that you're trying to maintain. If you get too close to here, this thing will attract to this and they'll stick together. And then the welding machine goes a little crazy and you have to unclamp from the electrode. All right. So learning to weld is a really cool thing to do. I really encourage you to do it. But it is very much an art form. It is, if you're not good, if your penmanship isn't very good, there's maybe a good chance that you'll struggle with this, because it is a hand-eye coordination type of thing. And there's an artistry. A really good welder can make a lot of money, but it is definitely a not just a science but an art. It's a very difficult skill to acquire, and it takes a lot of training, especially when you have to weld in other orientations. So when you're done with a weld pass, you'll have the slag, which is really a combination of what's happening with the shielding gas and also some impurities and that kind of thing. And what's left over from the not only the shielding gas, but this flux, right? And you have to chip away. You'll see it's kind of a fun thing to do, because it's almost like a coating that happens after when you're done with the weld. They're showing MIG and TIG, and I always forget what these stand for. We have, I think MIG is metal inert gas, and T might be tungsten inert gas. I think the tungsten refers to the tip, like the electrode is a tungsten piece, and then you add filler material as you're going along, and then there's this inert gas that's being blown in. So you really have kind of like three things that are taking place. You have the electrode that's causing the arc, which is causing all the heat. You have inert gas, which is flowing through here, which is making the shielded thing to prevent oxygenation of the molten metal. And then you also have this filler material that you have to feed in here. And for a lot of machines, you'll actually have a spool of filler material, and you'll have a little, well, they're not showing it here, but there'll be a feeding rate that'll going through here, and a lot of times it'll be foot actuated, so you'll also be using a foot pedal to be able to control how fast. You can also, I think, believe you could dial in the speed at which this wire filler material will contain, and that needs to be coordinated with how fast you are moving the electrode, and that has to be coordinated also with the temperature at which that you're keeping all of these things, right? So there's a whole bunch of things going on at the same time, and it's sort of a dance. So you can see right here where we have this. I believe over on the left is the MIG right there. But once again, the the arc or the electrode is not the same as the filler material in the MIG and the TIG. One could be wire fed through a machine. Another could be sometimes you're holding the filler wire over to the side. And the speed of the travel, the speed at which that you're moving the thing back and forth, the speed of the filler wire, and also the flow rate of the gas this can also blow the puddle away, so you have to be careful with that. And you also the amount of voltage or the amperage that you're putting into this. All of those need to be manipulated, and some of it has to do with the thickness of the material. Because if you have a very thin material, having too high of a temperature will blow by into the thing. So welding, you need to inspect a weld after you're done with it. And a good looking weld, like I said, will be like a stack of dimes, but that's very hard to achieve. This is a pretty decent looking weld, but you can't just tell how good of a weld is by looking at it. I mean, definitely if it looks poor, it is poor, but even within there, you could have a good looking weld and it could have defects. It could be the penetration might not be all the way through or as far as it's required. And there could be impurities. Not only there could be gaps in there, little pockets, other different things. So when you're looking at welds, I think I don't have the key for this, but this is in terms of this example. But A is probably a pretty decent weld. You can still see this is just there's still some randomness to the look. It would be nice if this was a lot more consistent and smooth operation. But it's you'd be amazed at how much your hand shakes when you go to when you go to weld when you see the end result. By the way, there is machine welding for very long strips of welds. You set the machine up and it automatically will move along at the right pace, but obviously you need to set those speeds up correct. If you go too fast, or maybe your electrode isn't hot enough, the bead might stick on top like you have right here and not penetrate deep enough. If you have it too hot, you'll undercut like here at C, and you'll get all kinds of spatter all over the place. You could also see that there was an inconsistent amount of travel speed taking place here. You get a little slow here, a little fast here. D doesn't look too bad to me, but then again, I don't have a key to this right here. So I don't know if there is something wrong with this necessarily. You do see there's little starts and stops. So you can't weld continuously all the time if you have a really long weld. So you have to be careful at the start and stops when you join a up again. This has a very bad pace. This is probably really fast and it's inconsistent speed. This is really probably too slow right here. You're seeing globs and it's inconsistent. You can see it's globbing up, and this is too thin. This is probably too fast as well. And you can see bad welds. The best way to judge a weld, unfortunately, is destructive testing. To actually take the weld and cut it apart, and then to etch it, polish it up, do some penetrating dye into it. And you could see there's these gaps inside the thing, and you could see that it's not penetrating all the way through. So these are bad welds. But unfortunately, the destructive test, obviously, you can't do that. So like if you're a qualified welder, you'll have to pass the test, and you'll have to maintain that qualification, and demonstrate different welds, and then they'll destroy those welds and then inspect to see if you're passing with the amount of penetration. So once again, it's a difficult skill, and it's an important skill to maintain. Here's a whipping of the whole. Actually, the speed of this right here, that you go back and forth in the zigzag pattern, will also determine what your outcome is going to be. And look at that! Look at that beautiful weld right there. Like that's a thing of beauty. That's like the stack of dimes that they're talking about. So let me end this show here and just go to a couple different welding videos right here. So I have them queued up to places I thought were important. I don't recall what they are.
Rust and mill scale could be a huge difference when we get into slag or heavy amounts of rust.
So he's talking about the, okay, so here's
Very
what...
smooth, decent bead. The sound to me was pretty crispy and pretty solid. It's round, the bead's rounded up a bit. Doesn't have any place for it to go. I'm just listening to the machine for stability. This was on a piece of clean material.
Okay, so I just wanted to, this is a MIG weld, I believe. That's the title of the thing, is the How to Not Weld, the Most Common MIG Failing Mistakes. I had this guy, this was a first lesson. Okay, so this is stick welding. So you can have, you can see what's involved here. And
let's concentrate on doing this.
all right, so there's a stick weld.
See some slag peel.
This is a stick weld. You see he's going to put it in the electrode.
Come on, darling, light up here. Don't be that.
This is probably the most difficult part of welding. When you first begin. He's not a beginner, but you can see that he's having a little difficulty. Is getting an arc started. It definitely likes to stick. A lot of times he's just getting it barely, so it doesn't stick right now. You would expect him to be a lot better at getting this started. But you can see that he's supporting it on his elbow right here. And it is very difficult, especially with this long stick, to not get the end shake. I'll mention something historically. These new shields, I don't know how long ago they came out, have a special screen right here that goes, that will be, you can see through it when it's not welding, but as soon as that arc hits, it'll change the opacity of the thing. We used to have to use the welds where you can't see through a traditional welding glass. It's too dark to see through. It's only when the arc starts to go through that you can actually see the arc, because you really need to protect your eyes from this. You will hurt your eyes if you look at a weld, so don't ever do it.
That way. Here we go. I need to explain what I'm seeing and what I'm feeling here. I have this rod leaned back probably about 40 degrees or so. I also have it pointed toward me about 10 degrees, just so I can get that slag running behind me. The whole weld pool, man, I'm barely touching the plate. I can feel the plate. Woo, there we go. Welcome to stick welding. I'll see what happened here. I've got a big old crack in my slag here. It just kind of fell off. So I've got an electrode that, not good, not good, not good. Got an electrode. You need to check the flux on them. I found some here lately that, I found a 6010 the other day. A 6010 the other day that had about, I don't know, about a third of the way up from the...
Now, you could not even see him making that motion. That's how subtle it is, the zigzag back and forth.
Start of the rod. I'm going to leave that little dingus on there and see if I can weld over the top of it. When I restrike this rod, I want to restrike it out here in the direction that I'm going. I want to kind of long arc lift over and bring it back into the top of this pool here and take off again. We're back in business. Again, I think I was just getting ready to say I'm barely dragging the rod, touching the material, barely. Last thing you want to do with one of these rods is gouge the plate. Now here's something to pay attention to when we come out here and terminate the weld. Please do not get into the habit of running this crater out here on the edge of the weld and blowing it up. Run the rod back in and fill that up a little bit. Please, please do that for me. It's good craftsmanship.
He should really, he's wearing glasses, but he should really be wearing some goggles as well, because that slag will bounce off your forehead and into your eye.
Not getting a slag peel, but it doesn't take much to get this off here. Okay.
And that's a decent looking weld. And let's see, lastly,
I'm going to run about 85 amps. And I'm just going to strike an arc and use a very slight rocking motion. Okay. Just back and forth and just kind of carry the bead along. That's all I'm doing. Real simple. Keeping the rod down close. Barely dragging the rod on the material with a very slight pitch. So this rod, the nature of this flux produces a, I want to say a light crystally type of flux. It doesn't come off real easy. It doesn't come off connected, I should say. But don't beat the out of it, because it can become airborne if you beat it. Come right back and stick in the lip or go in your eye. So generally let it cool. Scratch on it. Wire wheel with a grinder or hand wire brush, one or the other. This rod does produce a fair amount of spatter. That's just.
No, I don't like his weld. It doesn't look very pretty, but I think maybe he just needs to clean it up. So anyway, it's an interesting thing to check out. And I'll see continuing some more with things that you would want to know. Well, let me make another video. That was just the introduction to welding. Let's talk about welding symbols next in another video.